Welcome to developing low-power Meta devices with the nRF54L series. We're going to be talking about the different low-power device types, how to optimize your application for minimum power consumption, how to do the correct measurements yourself, where to find the correct introduction to do everything by yourself. We're going to be using the Power Profiler kit, and we're also going to have a look at the new online Power Profiler, where you can do the measurements without even needing your own hardware. And then we're going to go a bit more into which devices you want to use for your low-power Meta device. And with that, let's get into the recording.
The first of today's speakers is Kamil Kasperczyk. He's a firmware engineer in our Meta R&D team and has been working with Meta and integrating it into our nRF Connect SDK since the very start of the project. The second speaker for today is me, Finn Boetius. I'm a product marketing manager, and I've also been talking about Meta since it was still called Project Chip. I did mention that this webinar will be available later on. That also means that our previous Meta webinars are still available for on demand if you want to have a look at them. We did several webinars on Meta, for example, of a general introduction video, how to go to market with Meta, talking a bit more about the certification. And we also did a webinar on developing Meta products. So have a look at webinars.nordxamer.com, select Meta as an interest, and then you can have a look at all of our previous Meta webinars. And now let's have a look at the agenda for today. We're going to start off with Kamil talking about low power devices in Meta 1.4. There, Kamil is going to focus on intermittently connected devices and long idle time devices and their features. He will also talk about sleepy-end devices and I think a bit about synchronized sleepy-end devices. And then we're going to go more into Meta and low power support in nRF Connect SDK. How to do Meta energy optimized samples and configurations. How to perform current measurement with the Power Profiler kit. Kamil is also going to talk about our newly released white paper on energy consumption in Meta devices. And then we're going to go into our online Power Profiler that helps you estimate the power consumption on Meta devices. After that, I will be going a bit into power management ICs that fit Meta applications really well, including one for primary cell batteries, so non-rechargeable ones. Then we're going to go into the overview of the nRF54L series and why that is so well suited for low-power wireless designs. At the end of that, we will have time for the Q&A. But now let's get started with Kamil.
Okay, so let's start with a short introduction about low-power devices in Meta 1.4, as we're going to use 1.4 version as a base for this webinar, just to, build a common understanding on the topic before we'll get further in details. So Matter protocol uses term intermittently connected devices for low-power sleeping devices. In short, we usually call them ICDs, and if you think about the name, it makes perfect sense because Matter does not care whether the device is sleeping or doing anything else. It's just important it's not always available in the network. So it's just intermittently connected. Such a device can be in one of two states that we call active or idle. When the device is in the active state, we can expect that the device is responsive. In fact, it can be sleeping and become reachable from time to time because it doesn't need to have radio transceiver enabled all the time. But the sleep time should be that short to not cause visible latencies in responding. This state is designed for exchanging the data, and thanks to that, short sleep periods, we are able to exchange big amounts of data pretty fast, and then transit to the idle state as fast as possible. To save the energy. When the device is in the idle state, it can be less responsive or completely unresponsive, but it's obliged to become available from time to time so we could somehow finally reach it. And this state is used when the device has nothing to do. There are no expected exchanges, so it can just relax and save the energy. Let's take a look on the diagram, as it's easier to understand the exact ICD parameter definitions using an example. It presents example of current consumption chart, and the spikes are device radioactivities. So on the left, you can see periodical reporting case. the device becomes active to send periodic report. The interval between these spikes is very short, and it's determined by the fast pooling interval. And this interval decides about responsiveness on the networking level. However, we can also expect that the device makes activities on the matter level. For example, it sends periodic subscription data reports, and there is a separate set of parameters describing how often the device is active on the matter level. We have active mode duration parameter that says how long the device must remain in the active state. After that, it can switch mode to idle to save energy, but this is worth to emphasize that this is minimum duration. So the device can be active longer because, for example, it has a lot of messages to exchange. So the duration is prolonged until the all data are out, and we do not expect to get more of them. But sometimes it happens that for some reason the traffic was delayed, for example, due to the retransmissions, and we haven't got it on expected time. If we are going to sleep for a really long time, this could be a waste because we are going to exchange this information on the next wake up. So to prevent this situation, we have additional parameter called active mode threshold that tells us how long we should stay in the active mode after the last network activity. Like proactively wait for potentially unexpected traffic. So after all activities, the device switches to idle state and the interval becomes much longer. We have corresponding parameter that describes it, and it's called slow pooling interval because it's usually way longer than fast pooling interval. And it determines the responsiveness of a device in the idle state. And we have also corresponding parameter to active mode duration that is called idle mode duration. So in the idle mode duration, it determines how long the ICD can remain in the idle state. After that, it has to change the state to active and become more responsive. Again, it can also switch the state earlier if it wants to, because the idle mode duration is like maximum allowed time duration for the idle state, not like the exact duration. In the picture, you can see that the device becomes active again to send report after a few slow pooling intervals. In a real life, it would be probably much longer time, but it would not fit in the chart. So it's just an example. On the right, there is a different case. So the device is in the idle state. It keeps pulling. It's not the time to send report yet, but suddenly it gets asynchronous exchange from some other device. If it would be a door lock, for example, someone could want to unlock the door at this moment. The device is active for the data exchange time. It may be longer or shorter depending on the size of data to be exchanged, plus active threshold duration. And then it gets back to the idle state again. ICDs are divided into two groups as the way of handling communication has different challenges depending on how long the device is sleeping. So we have short idle time devices and long idle time devices. Short idle time devices sleep for less than 15 seconds. This time is short enough that we can expect that they are generally responsive, and because of that, the controller can reach it anytime. With, of course, some latency sometimes, but generally it makes sense that controller initiates the communication. The typical use case for such devices are actuators, so devices that are controlled by the user relatively often, such as, for example, a door lock. Long idle time devices sleep for more than 15 seconds, but it can be even several hours, as the upper limit for this configuration is 18 hours. Because of that, it does not make sense for controller to initiate communication and potentially wait like 10 hours for response. So it's assumed that an ICD initiates communication in this scenario. If it becomes available, it sends notification to all interested devices, like, hey, I'm here and ready to talk. And in response to that, the clients like controller can start data exchange. The typical use case for this scenario are devices that are not meant to be controlled, like sensors, as usually it's just enough to get periodical data reports with measurement updates. For example, it could be temperature sensor or smoke CO alarm. I will not spend more time on explaining SIT communication because it's quite simple, as the client just blindly sends messages and accepts the latency. However, for LIT, the communication is more complex. As I mentioned, the device notifies interesting clients in case it's available for communication. And to do that, it needs to support check-in protocol. Check-in protocol is sessionless, and it uses a secret key that is exchanged during client registration. If you take a look on the diagram, you will see that the LIT device actually does not always work as LIT, but it sometimes works as SIT as well. So it's not like a constant configuration, but rather a capability that can be used if some specific terms are met. So what are the terms? First of all, an ICD must have someone to notify. I've said that the LIT is not responsive, so registering the client would be very difficult in this mode. Because of that, ICD starts in unregistered state and uses SIT mode. After registering the first ICD client or getting the first subscription request, it moves to the corresponding check-in or subscribe states, and it can start working as LIT. I said it can, not it must, because the device may implement custom logic of switching to LIT, but the minimum requirement is having at least one client. The difference between check-in and subscribe state is that the device notifies about its presence using check-in messages or subscription data reports. Another useful and mandatory LIT feature is user active mode trigger. So you can imagine that you have your LIT working with a single client, but at some point you would like to, for example, commission it to the second fabric or change its configuration. As the slow polling interval may be very long, you will not be able to reach it just now, what is not convenient. The user active mode trigger feature allows you to make the device immediately responsive using some trigger that does not come from the network. For example, it could be a dedicated button press, power cycle, or for example, some sensor activity. LIT has also optional feature that is dynamic SIT to LIT switching. So it's always it allows to implement a custom logic that will decide when SIT changes state to LIT and opposite. Of course, respecting the specification requirements. An example. You can imagine that you have a device that is powered from a wire source, but it also has a backup battery. As long as it uses wire power source, we don't need to care about the power consumption, so it can be SIT. But in case of power outage, we can detect that the power source changed and make the device switch mode to LIT in order to save the energy and do not drain the battery. ICDs and their parameters have significant impact on the power consumption, but it's only a configuration on the matter layer. However, underneath, on the networking level, we also have some mechanisms that may impact the device behavior. So Thread protocol uses sleepy devices concept, and we have two kinds of such devices, sleepy end device and synchronized sleepy end device. The main difference between them is that sleepy end device uses periodic data pools to get the data from its parent. So it just sleeps and from time to time wakes up and asks, hey, are there any data for me? And the parent sends this data or not, depending if it has something in the buffer. And the synchronized sleepy end device does not ask for data, but it just wakes up periodically at the specific moment and listens for potentially incoming data. The parent knows when the child listens, and if it has some data to transfer, it will do that in the proper time slot. Both solutions have advantages and disadvantages. For example, sleepy devices occupy a radio channel no matter if they are data or not. So it can poll for long hours unnecessarily because no data were transmitted to it. And synchronized sleepy device does not do that. It just listens. On the other hand, sleepy device concept is so simple and so reliable that there are not many things that basically can go wrong. And synchronized sleepy device require really precise time synchronization with the parent because otherwise they will not match their time slots. And it will result in extending the listening time by the child and in the result wasting a lot of energy. So you can say it's a bit hard to predict what the power consumption of synchronized sleepy device will be because it's not constant. It depends on who it talks with. Sleepy devices are widely supported by all thread certified devices, and synchronized sleepy devices are not that widely deployed yet. So it may happen that the thread parent you have at your home simply will not work with this device well. To sum up, synchronized sleepy devices have some use cases that make it worth using. For example, they typically achieve lower power consumption than sleepy devices for very short sleep intervals, below 1 second. So the main use case for them are very responsive actuators, like for example, window roller shutter. So that's it for the introduction. I hope you feel more confident with your knowledge about ICDs now. Let's talk now about what Nordic Semiconductor delivers regarding Matter low power support. First of all, we deliver our nRF Connect SDK that includes various Matter samples. Several of them are energy optimized and they present different variants of ICDs and thread sleepy devices configuration. So let's open it. In nRF Connect SDK documentation, under samples, you can find Matter samples, and there is an array listing which samples by default enable what ICD configuration. So you can find there both SIT and LIT, and also thread sleepy and devices and synchronized sleepy and devices. The configuration that you see here are and examples that we provide for the specific use cases. However, you can change it according to your requirements or use this configuration for completely different device types that are not visible here. Besides of the Matter samples, you can also find a documentation that explains how to reduce the power consumption in your application. So we have information here about the ICDs and their parameters. This is partially the same information that I've presented today in the introduction. All ICDs parameters can be set using kconfig options, and their names are listed here. We have also config for active mode threshold, and of course for LIT configuration with all of its features. Besides ICDs, we have also description for how to configure thread sleepy devices and synchronized sleepy devices. And also we have timeouts that may affect how often the device wakes up, like MLE timeout or child supervision timeout. We have also several different configurations that are not dependent on the communication. So Bluetooth LE advertising, disabling serial logging, unused pins or peripherals, also configuring radio transmitter power or disabling RAM retention, and much more. Another source of useful information about Matter power consumption is white paper that we just released a few weeks ago. It's over 40 pages of comprehensive information about power consumption in context of Matter. So I really encourage you to spend some time on taking a look on that. The white paper is kind of guide that presents how to measure the power consumption with Power Profiler Kit 2 that is visible on the slide. You can also find, again, information about ICDs that you already heard today. We have also performed current measurements to different variants of Matter samples using different nRF SoC families and presented the results there. So you can use it not only to get data about our chips, but also compare them and see in what cases they are better or worse. All information are provided in a way that allows you to easily reproduce the setup and measurements either for one of Nordic DKs or your custom device. The white paper shows also how you can use the data from measurements to create simplified model and estimate the device annual power consumption. And based on annual power consumption, we can estimate the battery lifetime of the device. And in the white paper, we presented it for a few examples based on Matter samples from nRF Connect SDK. Without further ado, let's jump into the white paper. I will briefly go through sections one by one. So first we have a theory about factors affecting power consumption, like ICD configuration. You can find there all relevant information with nice graphics explaining the meaning of ICD parameters for SIT and also LIT. Moreover, we have also information about thread related factors, so explanation how sleepy device works, also the same for synchronized sleepy device, and for the thread child timeouts that I've mentioned before. Next section is setup for measurements. So basically it says what you have to prepare to reproduce the measurements. We have information here, for example, how to connect the PPK to the nRF DK, and also how to configure the PC tool for the measurements. What else? We have also here information how to configure the Matter application and what configurations we measured. So you can see these are 3 samples from nRF Connect SDK with few combinations of ICD parameters. 2 of them are SITs and 1 is LIT. Moving into measurement results, we have considered 6 scenarios that are Matter service advertising over Bluetooth LE, joining the Matter fabric, idle networking state, so the state when the device does nothing but only reporting, performing some simple exchange like handling write request, rebooting the device and reestablishing the connection, and also performing over-the-air software update. Every scenario has a table with collected measurements and also summary with observed dependencies. So what sample or which SoC is better for a particular scenario and why. Some of them also include screenshots from PPK presenting how the current consumption chart looked like. Once we have all measurements done, we can try to estimate the annual power consumption and battery lifetime. The white paper has some example of, let's call it, device activity model. So how often the device does specific things, like for example OTA or reboot. Then based on this equations from here, we can estimate the annual consumption of a device. And once we have the annual consumption, we can calculate, estimate the battery lifetime of a device that would be plugged to this accessory. We have results calculated for CR2032 battery and 2 combined AA batteries. yeah, and in result, you can see the estimated lifetime additionally, including the battery capacity reduction due to the environmental and aging impact. One thing that is worth mentioning here is that our estimations include only the current consumed by the nRF SoC with a radio running Matter application. And in the real products, there is much more hardware components that likely consume more current. So you must be aware of that. There is also a section that compares measurements done with chip tool and to commercial ecosystems to show if there are any differences in behavior of development implementation with real on-market devices. And finally, we have a conclusion part that summarizes all observations gathered in the whole document in a few paragraphs, highlighting the most important things. Yes, let's move to the more practical part now. I'm going to do the live demo and show you how to test the Matter ICDs and measure the current with Power Profiler Kit based on the same setup that is described in the white paper. So some prerequisites first. We are going to need nRF4L as a Matter accessory. I'm using nRF54L15, but you could also use nRF52840 or nRF5340. We need Power Profiler Kit 2 board connected to the DK using cables, and also Power Profiler application installed on the PC. And we need Open Fretboard router and chip tool as a controller when running. I'm not going to set it up now as it takes some time, and you can find the information how to do that under the provided links. I'm going to show you two examples. One is based on Matter door lock sample from nRF Connect SDK that is configured to work as SIT. It has slow pulling interval equal to 1 second and idle mode duration equal to 2 minutes. And the second example will be based on Matter smoke CO alarm sample from nRF Connect SDK as well. And it works as LIT. It has slow pulling interval equal to 30 seconds and idle mode duration equal to 15 minutes. By the way of presenting how LIT works, I will also show you the user active mode trigger feature and optional DSLS feature. I'm going to present you the scenario that I've mentioned before. So the situation when the device is powered from the wire source and acts as SIT, but after power outage and switching the to battery supply, it starts acting as LIT. Because I'm lacking battery supply for nRF54L15, I'm going to emulate power source changes. It could be done in various ways, but I have used test event triggers. So the Matter feature that allows to trigger custom behavior on the device from the Matter controller, what is very useful for testing purposes. You can find the documentation in nRF Connect SDK about it. Let's take a look on that. And if you scroll down a little bit, you will find the entries with power on and power off test event triggers for smoke CO alarm. And we are going to use them in the demo with the provided values for event IDs. I'm not going to show you the building and flashing process as it takes too much time and all the necessary configuration is described for this setup in the white paper. So I have everything already prepared to save some time. So once you have your board programmed and connected to the Power Profiler Kit, you are going to see the following current consumption chart. You can see there are a lot of short current peaks. It means that the device is advertising over Bluetooth LE and can be commissioned. I'm starting the commissioning using chip tool and pairing BLE thread command with thread network dataset and device onboarding data, so pin code and discriminator that I have obtained before. and it's done. You can see there were a lot of peaks and few white pulses that were related to data exchanges during the commissioning. And now we can see there are periodic peaks with 1 second interval, which is slow pulling, as you may remember. So it means that the device finished commissioning. Let's try to, for example, unlock the door and see what happens. I'm using now door lock unlock door command for the endpoint 1. And it worked pretty fast as the pulling interval is 1 second. So you can see here 3 wider peaks that are related with the data transmissions, and they occur with a 200 millisecond interval, which is fast pulling interval. So again, as you may remember, it means that the device switched state to active after receiving the first message and remained in the state to the end of data exchange. The duration of active state was quite short because there was not much data to exchange, and the active threshold duration is very small, as we don't need to prolong the active state because the device is generally quite responsive. Okay, let's move to the second scenario now. So the LIT, we have the same situation as before. So the device is advertising over Bluetooth LE, and we need to commission it in the almost same way. So let's again do it with the chip tool. So I'm using again pairing BLE thread command. The same thread network dataset, pin code and discriminator, but this time I need ICD registration true flag. This allows chip tool to automatically register itself as ICD client of a device, so we would not have to do that manually. And it's done. You can see the device does pulling now with 5 second interval, which is slow pulling in this case. Check. Yeah, it's 5 seconds, not 30 seconds as we configured, because it's in the SIT mode now, as we enable DSLS feature. Yeah, so as I've said before, we can use test event trigger to emulate the power outage. This is a part of general diagnostics cluster, test event trigger. We need the default key for the test event trigger and the test event ID. You can find both numbers in the documentation I presented before, and it's for endpoint 0. So this command emulates disabling wire power source, so the device should switch to battery source and select ICD mode to LIT. First, you can see big group of peaks, that is command reception plus active mode threshold equal to 5 seconds. And then nothing. We need to wait a bit for activity because slow pulling interval is 30 seconds now. This small peak that you see here is not data pull, it's only a peak from the timer, so we can ignore it. And finally, we have it, and it is 30 seconds. Yeah. LIT also supports active mode trigger feature. In this sample, it's triggered on the button press. So you can see the device is sleeping. I'm pressing button number 3, and it becomes immediately responsive because the interval was changed to fast pulling. Now you can, for example, easily reconfigure it or commission to the second fabric. And that's it for the measurements. I hope you find it consistent with the theory we talked about. All the steps are documented in the nRF Connect SDK documentation and also in the white paper. So I hope you will not have any problems with reproducing this setup on your desk. Let's get back to the slides, as I have one more cool application to present. We believe that all tools and materials that I have presented today are useful, but you always need some hardware to test it. And sometimes you would like to check something really fast. You don't have DK nearby. Like, for example, hey, what would happen if I change this parameter from 200 to 500 milliseconds? How much longer my device could work on the battery? Now you can do that using our online power profiler for matter over thread. This is an online tool that allows you to estimate the power consumption. It is based on a theoretical model of ICD behavior, and it is supplied with measurements data we obtain for you. It supports different nRF SoCs, voltage supplies, and TX power levels. You can adjust your ICD parameters and also see how they affect the behavior. So that's it for the inputs. Regarding the outputs, it presents the average current consumption during the sleep state and also during the single thread data pool. But you can also use it to estimate the total power consumption over the given time period. So you could use it, for example, to check how much energy will your device consume over a year. And then based on that, compare with capacity of some battery and estimate the lifetime of a device supplied by this battery. And the tool also prints model of current consumption chart. So you'll find it similar to what we have already seen on real measurements from PPK. Let's take a look on that. Yes. So on the left side, there is a configuration that you can adjust. We have 3 SoCs, so nRF5830, 5340, and nRF54L15. That TX power, which is 0 dBm, and max available power. For example, for 54L, it's 7 dBm, but for 5340, it's 3 dBm. And the voltage supply, that is 3 volts or 1.8 volts. Then we have ICD configuration. So first you need to choose whether the device is SIT or LIT, as it brings some limitation to the values of parameters below. Every ICD parameter has a hint with explanation, in case you would forget what does it mean. And at the bottom, there is operating time, so you can use it, check how much power the device is going to consume over this time. The outputs are at center, so we have average charge for a single data pool, average sleep current, and also average current consumption over the whole time. And also we have total consumption, total consumed charge over the time you have selected. And finally, there is a model of current consumption chart. You can see we have green peaks that is slow pulling in the idle state. Then 2 bigger blue peaks that are related to the subscription data report and acknowledgement. And then there should be smaller blue peaks for the fast pulling, but maybe it will be better visible for LIT. Yes, because it has bigger active threshold duration. So for example, you can change the slow pulling interval, for example, to from 30 to 60 seconds, and you can see that there is much fewer green peaks here. I can also change, for example, the duration to see if this total consumed charge changes. So now it's 16.5. So let's change it like twice. Yeah, and you can see it's 2 times bigger than it was before. I can also change, for example, the TX power and change it back again. And you can see that the total consumed charge is greater for the bigger TX power. But interesting thing is that the slip current is not changed because the TX power change impacts only the radioactivities and it does not impact the slip current at all. So that's it for this part. I hope you enjoy it and you find it useful for designing your own products. I'm encouraging you to play with the presented tools and use the materials. Thank you. I'm passing the voice to Finn that will tell you more about Nordic products that are not necessarily applicable only to Matter.
Yes, thank you, Camille. Not only to Matter, but very relevant for Matter. So I'm gonna start off by talking a bit about power management ICs. So let's have a very quick overview of what actually a power management IC is. If you want to think about it, it's basically you have a little black box, it gets some power inputs, so you get a DC supply voltage, you have battery power and maybe some battery charging, and the output of that black box is some regulated power. But if you want to make PMICs a bit more interesting, you could also add some extra features. An example of that would be some system management features that we included in our NPM1300. So let's have a look at that one first. At its core, the NPM1300 is an ultra-high efficiency PMIC with a unique system management features. For example, it offers really accurate fuel gauging. So if we look at the diagram here, you see there's some useful features integrated. For example, you have a hard reset. You have some normal features that you would expect in a PMIC, for example, the load switches and LDOs. You also have this digital interface that, for example, allows you to use some of the GPIOs on the PMIC, or that allows you to use some of the pins on the PMIC as GPIOs for your host processor. So there's a good reason the headline here is actually the most intelligent PMIC on the market. Some of the extra features that you can get with that is the failed boot recovery. You can have this really nice hard reset functionality, which also means you can use some of the GPIOs that are on the PMIC to enable normal functions and then use the same GPIO to also enable a hard reset, for example. You have a really nice hibernate function that runs a timer that just consumes nanoamps of currents. You have external watchdog timers, and you also have a power loss warning. You have a bit more wiggle room when you have the power loss warning on an external component like a PMIC. So usually there's some extra energy left that you can use to get your SoC into a safe state when you detect the power loss warning early. So when you detect it on the PMIC level, not on the SoC level. So yes, that was the NPM1300, and I'm going a bit faster because I'm trying to get the webinar done in time so that we have enough time for a Q&A. So the next one we want to talk about is the NPM2100. And this one's a PMIC for, as I mentioned before, primary cell batteries. Primary cells have several challenges if you want to use them. So it's about finding an efficient and flexible boost converter, and you want to reliable estimate how much energy is actually left in your battery. Then again, you also want to achieve very low standby power, and you want to be able to ship products with the battery inserted if you can. A way to do this oftentimes is just this little plastic flap that you see jammed in between the connector and the battery. With the NPM2100, you actually are very close to the same power consumption of that little plastic flap with the ship mode. So let's have a look at the NPM2100. And this one's especially interesting because we see a lot of smart home applications actually run on primary cell batteries. So this one's targeted at very low power wireless applications. Usually this is something like Bluetooth or Thread. And it has dedicated energy saving circuits to save battery life. So it has an ultra efficient boost converter, so you can actually get the most out of your battery, even when the voltage would be too low to still drive your MCU. So you can run the whole application off one AA battery, for example, or AAA if you want to. It has a really, really low power consumption hibernate and chip mode. It's very, very compact, so it's less than 2 by 2 millimeters in scale. And it only needs 6 passive components to work. Yeah, so this is the very brief overview of the two most relevant PMICs, in my opinion. Here's an overview of all of our PMICs. I grade the ones out that I don't think are very relevant, at least not for the topic of this webinar. So, very quick summary, the NPM 1100 we didn't talk about, but it's basically the very efficient and the most simple battery charging PMICs that you can imagine. It charges with up to 400 milliamps. So you can expect to have like a 400 to 800 milliamp hour battery, and it'll be charged in 1 to 2 hours. So that's completely fine for most applications. If you want all the nice system management features that I talked about, the NPM 1300 would be a good choice. And if you have non-rechargeable batteries, so if you're running on primary cells, the NPM 2100 is a really good option that you should take a look at. Okay, and with that, let's get over to the nRF54L15 or the nRF54L series. Okay, so let's put it into perspective. I'm guessing most of you are familiar with our 52 series of wireless SoCs. If you're not, this is probably the most used Bluetooth LE SoC in the world. So we are selling this in billions per year. It's basically a microcontroller with an integrated Bluetooth radio. That's the most high level description I can manage. This one's what's really like used in most Bluetooth LE applications these days. Then you can have one step up, which would be to a dual-core wireless SoC, so our 53 series. This has a dedicated application processor, an extra radio processor, and also has extra memory and does things like, for example, support Bluetooth LE audio. This is also a really nice choice for some more demanding meta applications. But what we want to talk about now specifically is the 54L15, which has a relatively similar feature set to the 52 series. So it's very fair to say it's going to be its successor. It basically supports the same use cases plus a bit more. But the really big thing here is that the power consumption is drastically lower than the 52 series. And this is depending on the use case. I mean, there are use cases where you literally consume a third of the power, but that's not really a real world scenario. So you can expect about 30 to 40% in your application, depending on what you're doing, while having about double the processing power. If we have a look at the next page, we see where double the processing power comes from. It's from double the clock speed. And next to this more processing power, we also have the 4th generation Nordic radio in here, which is the new Bluetooth radio that's more efficient than the old one. And we also offer advanced security. By the way, radio, there's obviously also a thread radio in here that can also be used for Zigbee, for example. It has a comprehensive set of peripherals. It has some high-speed serial interfaces like SPI and UART. It also has an extra coprocessor in here that's marked in the diagram with RISC-V because it's a RISC-V coprocessor. And then we also offer different memory configurations from 1.5 megabytes down to half a meg, and also different versions with different amounts of RAM. All of these options will be pin compatible to each other, not to 52 series. How do you get that much more processing power while also consuming less power, you might ask? The easy answer to this one is we went down to a 22 nanometer process node for the low power architecture. So we get the double processing power, mostly from double the clock speed, but also the smaller technology makes the SoC in general more efficient. So if you have a really extreme use case like here, where, for example, we're just doing heavy computing, you actually get to about 3 times the processing efficiency. And since we are now really running out of our time, I would like to finish this with letting you know that there is a specific webinar just on the 54L series that's also available on webinars.nordexami.com. So now let's get over and have a look at all of your questions in the Q&A. Good. And the very first one I already started with. Let me just also get this on. Okay, here we have it. Can you also share the link to the white paper and the power profiler? The white paper we already shared earlier in chat, and now I also just put the link to the power profiler in there.
User active mode trigger, can this one be triggered from the device? Is this supported by most ecosystems? So generally the idea is of this feature is to trigger it manually by the user, not remotely. As remote triggers over the network will not work because the device is sleeping, and our goal is to like sort of interrupt its sleep. So basically, we can't do that over the network. Currently, ecosystems do not support LIT at all yet. Because it's quite a new feature. So also user active trigger is not supported. But yeah, as I've mentioned, this is not like the feature designed to be used for over the network. So I would not expect that controllers are going to support it ever. Okay, so if I have a synchronized sleeping device, do I need to prepare it to work as an sleeping device in case synchronized sleeping device are not supported by the border router? So it's not like border routers. So border routers have to support synchronized sleeping devices. Otherwise, they would not be threat certified. So it's not like it does not support it at all. It may not support it well. So the accuracy of synchronization will be bad. And because of that, the power consumption of synchronized sleeping device will be quite high. So currently there is no such, let's say, adaptive selection. So if we have synchronized sleeping device, it always works as synchronized sleeping device, and it will not automatically switch to sleeping device based on some accuracy criteria. But yeah, this is something that we also considered, and probably it could be evaluated and used as some future plan for the improvement.
Is it possible to keep a device in system off mode to save power consumption and then make the device wake up on an RF event? So the answer is yes and no, basically. So the short answer is no. The long answer is this is how you would expect it anyway. So you can schedule something prior to an RF event and then make sure it is ready to receive, but you can't make it sleep and then just wake up on the RF. I hope that answers that question.
We want to build Matter over Thread gateway. And a suggestion, which SoC or module shall we use? So there is no like simple answer to this question, I think, because I'm not sure what this gateway is supposed to do. So is it a gateway with the cloud connection, or did you mean bridge between Matter over Thread and some custom protocol? So if it's about a bridge, we have a sample application that presents how to implement the bridge between Matter and Bluetooth LE, for example. It can be also used as a base for creating a custom solution. So it works with nRF54L DK. So I would say that nRF54L should be the best option for now due to the available flash and RAM. But basically the selection depends on your requirements related to the memory.
Okay, thank you, Camille. And then we have two questions who kind of belong together. I'm just gonna put the second part in here. Does Nordic provide any implementation or demo document on how to achieve a Matter over Thread gateway with a Linux host? This goes together with a question that's asking about doing it on Cortex-A and then in combination with something like KNX IoT, which makes sense because KNX IoT also is using Thread. Here again, this has a short and a long answer. So the short answer is no. If you would want to do that, you would run the main applications on your Cortex-A and then use one of our SoCs as the extra SoC next to it to add Bluetooth and Thread functionality. The longer answer is we have several partners in our Nordic Partner Program that can help you, and some of them are also like specifically mostly working on Linux. So if that is something that you're interested in, we can get you in contact with one of them. But our focus isn't developing on Linux. We have partners that are a lot better at that than we are.
Then I have one question that has the email address of the person asking it in it, so I'm not gonna put it on screen. Let me just read this out. So we are a hardware manufacturer for windows and door locks with lots of electronic devices, access control, and we want to expand our ecosystem, adding Meta. We could begin to add this protocol with a door lock demo. Where can we find all the materials? Is there something specific that we could discuss? My email address is... okay, so the best way to start would probably be our Meta door lock example. Let me just copy this in the chat, I think. And we can also set something up afterwards, since we now have your email address. Oh, did I? Yeah, here it is. So there's the technical documentation for the door lock. That is something you can start off. If you're specifically looking at door locks, you might also be interested in the upcoming Aliro standard, which is a standard specifically for door locks. But then again, that's probably a bit more than we can discuss in this one webinar. But yeah, we will contact you, and this is definitely something that we can help with.
So do you follow or help customers during Matter certification? There are much aspects of firmware MCU hardware to respect to pass the certification. I don't think like we can provide dedicated regular help to every single customer approaching the certification, but generally in the past our customers were putting the questions and requests for help on our DevZone portal. Our tech support team handles it for us or reaches the Matter developers in case of like more complex cases. And in the past, we also escalated the issues to the CSA certification group if we decided that customer found some bug that should be fixed. So generally, I think that we can say we are helping with passing the certification.
Yes, and then there's also again things like partner companies. For example, we have like some of our module partners offer you a bit more support on that front, even up to actually like selling you a pre-certified module that has your Meta application on it and has the device attestation. If you're more interested in that, we have a webinar on specifically this one in 2 weeks. You can already sign up for that on webinars.nordexam.com. I'll also put it on the screen. Okay, so this one's answered. Here's one more about the KNX IoT, which is also thread-based again. How do you suggest we add a simple prototype with your KNX? Oh yeah, this is the webinar, by the way, in the background. Sorry. So if you want to get started prototyping, and I think this is the follow-up on the question about the combination of Meta and KNX IoT, I am guessing an easy way to do this would be to take one of our 52840 dongles. That's basically a USB dongle that you can plug into your device. That is also how we used to make our own thread border routers. Basically, you add one of those to a Raspberry Pi, and then you can make it into a thread border router. So there's ways to do it. Probably the dongle is the easiest way if you want a fast prototype.
How much time a LIT device can sleep to maintain thread connection? So generally by the Matter specification, the maximum time of sleep is 18 hours. However, it's like the interval on the Matter layer, and to like maintain the thread connection, there are also other parameters like MLE child timeout and also child supervision timeout. So in case we want to set like big sleep intervals for ICD, we have to also remember about increasing the timeouts on the thread layer as well to make sure that parent knows what it should be, what is expected. What happens if you add a LIT device to the Matter ecosystem not supporting LIT? So it's just going to work as SIT with the biggest interval allowed for SIT, so 15 seconds. It's because, as I've presented in the demo, if the ICD LIT always starts as SIT and waits in the state for registering the first ICD client. If the ecosystem does not support LIT, it will simply not register as a client. So the device will keep working as SIT.
Then the next one I can take again. It's about Meta over Thread again, but with a Linux host.
Does it mean we need the thread RCP? In that case, does the 54L still the best option? So as I mentioned, like for the prototype, it's probably easier to take the dongle. For the final device, I am guessing the 54L will be your best option for that, because it's not just the 54L15, right? You could also go to a smaller version like the L10 or the L05, depending on what you want to do. It's very hard to like definitively say that without looking at what you're exactly gonna do. But most likely, yes. So then we have one more question that's kind of a very broad question. What are all the security features that Nordic IDE or SDK provides for IoT products? So this is not easily answered in one sentence. So the important thing here is probably everything that Meta requires. And more. So it also depends on which devices you're using, but in general, the 54L15, for example, is it has all the features that you would need to get the device PSA level 3 certified, for example. Can I develop Meta devices without being in the CSA? Camille, do you want to take this one?
You can develop it, create like some proof of concept for your purposes. However, you will not be able to certify it because to approach the certification, you have to be a member of the CSA. So I would say that to get some product to the market, you would need to be a member of CSA.
Do we have a power consumption comparison between the 5340 and the nRF54L for the same application to benchmark the improvement? And can we share?
I've seen this question and came early before we even started the presentation, so I think that we have already answered in our presentation. There is such a comparison before 5340 and 54L15 for free sample applications and different configurations. It's in the white paper. It's also compared with 52840 in case you would need it. You can also use this online pair profiler to compare it fast, but I would say it's better for really fast comparison, and white paper is better for like deeper analysis.
Which PMIC can I use if I have a 600 milliamp lithium polymer battery? Well, in this case, it would probably be the 1100 or the NPM 1300, and that completely depends on what you want to do. Like in addition, do you want the PMIC to just be a battery charging PMIC and do basically nothing else, just be very small, very efficient? Then you would go for something like the 1100. And if you actually want the system management features, like if you want something like an external watchdog, if you want really accurate fuel gauging, if you want to have a hard reset, that's also a GPIO. Like all of those features, basically, like if you wanted to do more than just battery charging, the NPM 1300 is something you can definitely take a look at. I think we also have dedicated webinars on the same topic. We have development kits or evaluation kits, they're called, I think, for the PMICs. So there's enough resources to like get started, test it out, and see if you want to use the system management features that the 1300 has.
Yes. So can I use ICD formatter over Wi-Fi? Well, we don't support ICD with Wi-Fi for now. It's because the Wi-Fi communication in Matter strongly relies on multicasts, for example, for DNS. And if the device is sleeping, it can miss multicasts, and there is no one to buffer these messages because access point buffers only unicast traffic. In practice, we have something that we call low power Wi-Fi configuration that makes the device keep every few beacons and sleep for a short period of time. It's called DTIM, I think. But these periods have to be really, really short to like minimize the risk that we will miss the multicast frame. Yeah, however, something that could work and we would like to evaluate it in the future is using Wi-Fi for ICD LIT because LIT initiates communication. So theoretically, there would not be the situation that we can get like asynchronous frame without being prepared.
We got one more question in, Camille. I hope you can answer this one. I'll just put it on screen.
Mm-hmm. Are you planning to explain a little bit about other ways for commissioning like NFC? If you mean the NFC commissioning, so the initiative that is handled in the CSA, I believe it's planned for the Matter 1.5 release. We are not going to be involved in NFC commissioning specifically because as a manufacturer, we don't have NFC chip can make right operations, so we don't have basically hardware to perform NFC commissioning. Yeah, I hope it answers your question.
Yeah, so the confusion might be because like we have chips that have the NFC-A tag functionality, but if the requirement is having NFC host functionality so that the other device can, for example, get powered, that's not something that our chip allows. So we can be, well, our chips can be an NFC tag, but it can't be an NFC host. So for that, you would need an extra IC next to it. You can still do that and use one of our microcontrollers, but you will need an external IC next to it to do that. You can probably, and Camille, correct me if I'm wrong, you can probably use NFC to establish a Bluetooth connection. So instead of the QR code.
Yeah, so you can use NFC tag for like sharing onboarding information. So instead of scanning QR code or putting manually the manual pairing code, you can scan NFC tag, and we have support for it now in our samples, but it's just like sharing the initial information about the device before starting the commissioning over BLE.
Yeah, so you would still use Bluetooth. The NFC host in that case would be your phone, as it is when you scan a QR code. And then you're still using Bluetooth and Thread. So like there you would have, like if that's what you're asking, can I just tap my phone against the device and use that for commissioning? That is something that our chips should be able to do, if I'm not wrong. Good. And then I have one more that's not in the questions, but is in the chat. That's about if we're going to share the presentations. So what I'm going to do is after this webinar is over, we're going to upload it, make it available on the page that you used for sign up and on webinars.nordicsamurai.com. And there we'll also have all the materials. So for example, the links that we shared here in chat, the recording and the presentation available for you to have a look at later.
Sorry, I think that we have one more that we missed. It's also in the audience chat. It's about is there a LITS synchronized CPN device? So maybe I will answer it fast. So I don't think that LITS synchronized CPN device makes sense because LIT usually have quite big sleep interval, and synchronized CPN device is not performing well for such big intervals because it has to exchange some data with parent from time to time to keep synchronization. So it makes sense to use synchronized CPN device only for small intervals to don't get this additional consumption coming from the maintenance. In practice, it's better than CPN device only for values smaller around 1 second and smaller. So yeah, very responsive actuators.
Perfect. And then I'll use this opportunity to tell you that we have another webinar on Matter coming up in exactly 2 weeks. It's called Lowering Barriers for Matter Device Production and Certification. So basically what this is about is pre-certified Matter modules. This is the very brief summary of it. So we're talking about the pre-certified modules and how you can actually get a programmed and certified module from a partner like Panasonic in this case. So that one's gonna go a bit more into certification also of Matter. And with that, no more questions. Then I want to thank you all, and we'll update you when the recording is available. Okay, thank you, bye.
Thank you.